This is a short presentation on Scalable log determinant for Gaussian process kernel learning, a paper appearing in NIPS 2017. My name is David Eriksson, a PhD candidate in applied mathematics at Cornell University, and this is joint work with Kun Dong, David Bindel, Andrew Wilson, and Hannes Nikic. In this paper, we discuss an efficient method to compute the log determinant and derivatives of a large kernel matrix. This is an important computation that arises in many applications, including Bayesian model comparison, Bayesian deep learning, determinantal point processes, elliptical graphical models, and kernel learning for Gaussian processes. Recall that a Gaussian process is a collection of Gaussian random variables indexed by spatial position, where the covariance between any pair of points is given by a kernel function little k. This kernel typically depends on some hyperparameters, which we denote by theta. In regression, we assume y are noisy observations of the Gaussian process at points x. Given y, we would like to infer values at other points. In kernel learning, we would also like to learn the best values of theta. In the maximum likelihood approach to kernel hyperparameter learning, we maximize the log marginal likelihood of the data given the hyperparameters. To do this, we need to evaluate not only the quadratic model fit term, but also the complexity penalty. Naively, this seems to require dense matrix operations that require order n cubed time and order n squared space. However, if we only cared about evaluating the model fit, we could apply an iterative method relying only on fast matrix vector products with k tilde. The question is, can we accelerate the computation of the log determinant and its derivatives in a similar way? We begin by writing the log determinant as a trace of the log, which we can compute using stochastic trace estimators. Moreover, we parlay fast MVMs with k tilde into fast MVMs with log k tilde using the Lanczos process, a common tool for computing eigenvalues in matrix functions. As it turns out, the gradient of log k tilde can also be expressed in terms of traces of certain functions of k tilde, and the same Lanczos steps can be used to compute gradients. The Lanczos process is sensitive to the locations of the eigenvalues of k tilde, and hence this method tends to yield much better accuracy than so-called Chebyshev methods, which instead use a polynomial approximation of the log. There are several possible methods to compute fast matrix vector multiplies with a kernel matrix. In our experiments, we typically use the structured kernel interpolation method SKI, which uses a scale eigenvalue approach to approximate the log determinant by taking advantage of fast eigendecomposition for Toeplitz matrices. However, this structure is not always available, and this method does not work for sums of covariances or non-Gaussian likelihoods, areas where our method still applies. We illustrate the suitability of the method for non-Gaussian likelihoods via regression and kernel learning for a log Gaussian Cox process used to model counts of hickory trees in a forest in Michigan. In the figure below, we show the raw data and a heat map of the predicted count using 3 different methods. From the figure, it is clear that the exact approach and our approach produce very similar predictions, while the scale eigenvalue approach yields significantly worse results. In summary, our paper develops a highly effective approximate solver for computing the log determinant of a kernel matrix, along with derivatives. Our approach is more general than prior methods, as it only depends on fast matrix vector multiplication. We have released code and tutorials as an extension to the GPML library in MATLAB and as a part of GPyTorch in Python. If you have any questions about this approach, please come talk to me at the poster. Thank you for listening.